a single part that could be configured across, instantiated across a surface to create a whole a structure. And so I suppose a good way of describing these types of things, think of that, is that although they're not the same dimensionally, they all contain the same kind of DNA. And that DNA plays itself out, but the dimensions change. Also known as a power copy in CATIA speak. We were also studying how to flatten this, because this project was intended originally to be made out of folded metal or folded plastic. There, difficult to see a gridded array of unfolded pieces of this material, which could, in theory, in this case, have been cut out by some kind of CNC machine, laser cutter, water jet cutter, what have you. I also think they look like space invaders. We're studying sort of the kind of proof of concept of this in model form. Again, this is a PETG folded flanged assembly prototype. It's about 6 feet long.
I mean, one thing that you will notice, we do make a lot of prototypes. We basically prototype almost every single, or not every single, but we prototype ideas that we think are worthwhile seeing in a different form, built form, and learn from them. See what they tell us, and go forward with that.
Especially at the time when I was working on this thing, we weren't even thinking about this thing. The Maximilian Shell project ultimately became a minimal surface in the same type of structures that Otto's working on. This wasn't the case. It's quite an elaborate process to get there. So we're taking it a little bit further and trying to develop a way that could be more rapidly prototyped. In this case, we're imagining it out of folded paper. So there's your part. There's your kind of minimal surface, which I can call a virtual surface. And then once it's instantiated with these parts, becomes kind of the structure. And at the time, we're playing with this notion that because these were the type of tools we were using, we imagined that they could become this system which would, because it's so easy to make these things very quickly, this being something made out of paper, that we could essentially create a kind of a made-to-order product that a customer could stretch and pull virtually, and then we print out the parts or have them cut out, and then assemble them and put them out rapidly. That's my cat. Dust mop. She was the inspiration for this. Well, okay. So one thing that we did notice though, this is that now this is a really ugly lampshade thing, but it is just kind of proof of concept. We had to give it a function. I remember he came over to my house and he looked at it and he's like, "What the hell is that?" And I was like, "Well, it's the concept, man." He's like, because it doesn't really do much as a lampshade either. I
bet you put it upside down too.
Is it upside down? No, that's correct. Okay, so well, what doesn't work when you go up in scale on something like that is that a flange connection, because it's like this, is not going to work. It's going to pull apart.
So from looking at the folded model, you can see that thing, and you just thought if this thing jumps in scale 100-fold, it would work. It's just not going to work. So
the stresses on the connection start becoming really, really big. So we have to explore a lapping system. So it was
in a different material.
And a different material that would lap. I mean, you probably could have lapped that with polypropylene. Polypropylene, if anyone doesn't know, is the stuff that they make Tupperware out of. Vinyl? No.
Vinyl.
It's all plastic. So we after a really extensive search, we started looking for materials that came in rolls as opposed to sheets. We came up with this reflective mylar that is some very interesting qualities. It's simultaneously transparent and reflective, and it has the strength, tear resistance of a lot of woven fabrics. And then also it has this ripstop to it, so in the event that, which are those little X's that you can see, so in the event that one were to put a hole in it, the hole will never extend beyond that. So, we're working out modeling for it. There's one of our famous renderings on the right. Just stunning.
Really?
but actually the model from which it was derived on the left, which is a fully linked associated parametric model that we were using because we weren't quite sure how big this space was going to be, so we would stretch how big this thing was going to be. So we'd stretch the whole model and all of the parts would update, which was very satisfying in its gee whiz kind of way. There is kind of the way that what we're talking about. You have a skin assembly made up of multiple parts forming a three-dimensional object, and then this array of parts that are nested and cut out. This is a machine that we use, and I was going to behave. Oh yeah. Which is a CNC fabric cutting machine, which is the reason we chose this is because it is able to cut roll material at about probably 1/10, maybe 1/20th the cost of laser cutting.
All based on speed. I mean, if you see the rate that machine is moving, and any of you guys that are familiar with CNC equipment, most of it doesn't move that fast. And it's a function of time, but it's also the time costs money. So the more time that you spend running that thing, the more money it costs. And this thing looking quickly through.
And it was designed, and the material that we use is really typically cut on these types of machines every day, so it was not, there was no surprises in that respect. Nested parts. Started to explain, there you can see the machine that we do. We started playing with actually trying to trick these machines because they actually mark the material as well with a Sharpie. And I started thinking, like, well, wouldn't it be fun to try to make it draw? It's like a hand, sort of. It's a mechanical hand, it really is. And so, I don't know, I think that picture is actually, what's the guy, is it from Save?
It's the guy, he's going to Save. It's Dustin Hoffman, maybe running
it's in Marathon.
Marathon.
Yeah. I had to turn him into a font. I got him from a horror fonts collection on the internet, and then we turned it into a font, and that was able to trick the machine into drawing it. But it actually took quite a long time to draw, so we nixed that idea. But you can see there's an elaborate labeling system on these parts there. Regarding he's Zell. Zell.
This is safe.
Yeah. That's when he's going to give him the injection in second part. Yeah. So there's also an elaborate marking system because these parts, this project is made up of 504 separate parts, and each of them is unique, and they all fit together in exactly one place. So this requires a very elaborate labeling system, which also prevents you from getting out of sequence.
And we were exploring drawing as part of that labeling system.
All right, these are all early prototyping. Another prototype that we made in the backyard, studying the light conditions. This was kind of our home do-it-yourself study of tension. Neither of us had worked with tension before, so we had no idea what a cable would do stretching 65 feet. Yeah.